In this section, we're going to talk about acid-base theories. So it turns out defining an acid and a base is not that easy. There's not one definition that works great for all scenarios. So we're going to learn two of them that are commonly asked on the Regents. The first one is called the Arrhenius definition. So this was invented by Svante Arrhenius. He said that acids produce hydrogen ions in aqueous solutions. So he would say that HCl would be an acid because when you put it in an aqueous solution, it dissociates into hydrogen ions and chloride ions. So the fact that it gave off hydrogen ions is what makes it an acid. He said that bases produce hydroxide ions in aqueous solutions. So sodium hydroxide would be a base because it dissociates in water to make sodium ions and hydroxide ions. So the fact that this substance gives off hydroxide ions is what makes it a base. So table K and L on your reference table have some names and formulas for common acids and bases, and you'll see that most of these fit the Arrhenius definition. Our table K here showing the common acids, they all have, not all, but all of these have hydrogen ions. So when these go in solution, these hydrogen ions will dissociate and go off into solution. So these would all be Arrhenius acids. If we look at our list of bases here, most of them would be Arrhenius bases. They have hydroxides in their formula, so when they go into aqueous solution, they will dissociate and give off hydroxide ions to solution. But we have an example here that doesn't. So ammonia acts as a base, but it does not fit the Arrhenius definition of bases. So there, like I said, there's some issues here. This is also limited to just aqueous solution. So if you have a scenario where you don't have an aqueous solution, the Arrhenius definition doesn't work. Also, it limits bases to only one kind, hydroxides, and like we just saw with our reference table there, ammonia acts as a base, and it is definitely does not have hydroxide in it. Also, not all compounds that have hydrogen are acids. So the ones on our table are, but there are plenty of compounds that behave like acids that do not have hydrogen in them. So we need another definition for these scenarios. So there's another definition called the Bronsted-Lowry definition of acids and bases, invented by these two guys here. And the Regents, for some reason, will never say Bronsted-Lowry. I don't know why, but it will say an alternate acid-base theory. So this is your code word on your test questions to switch over to Bronsted-Lowry definitions if they say an alternate acid-base theory. So in the Bronsted-Lowry definition, acids are hydrogen ion donors. So they give off hydrogen ions. This actually doesn't change from the Arrhenius definition whatsoever. Arrhenius definition says they give off hydrogen ions in solution. Bronsted-Lowry says the same thing. They are giving away hydrogen ions. So they're donating it to someone. Rather than just giving it off the solution, they're donating it. But it's basically the same. In the Bronsted-Lowry definition, bases are hydrogen ion acceptors. So our definition is solely on what's happening with the hydrogen. If you're donating hydrogen, you're an acid. If you're accepting or taking in a hydrogen ion, you are a base. And another thing about the Bronsted-Lowry definition is that acids and bases always come in pairs. So let me show you what I mean here. So a conjugate base would be the pair of from what the original acid becomes after it donates its hydrogen ion. So you have the acid on one side of the equation, and then you have what the acid becomes after it donates the hydrogen ion. We call it now the conjugate base. So it switches. The acid becomes the conjugate base. And the base becomes the conjugate acid. So the conjugate acid is what the original base becomes after it's gained its hydrogen ion. And you're often asked to identify who are the acid, who are the base, and who is the conjugate acids and bases in equations. So here's an example here. Hydrochloric acid plus water makes a hydronium ion and chloride ions. So if you're asked to identify who's the acid, who's the base, who's the conjugate acid, who's the conjugate base, all you need to do is follow the hydrogen ions. So HCl on the left, my reactant HCl, if I look at what happened to it on the right, it's lost a hydrogen ion. It's become Cl minus. That means it must have given away or donated its hydrogen ion. The only one it could have given it to is the water. So let's look at it. If we give this hydrogen ion to an H2O, what does it become? It becomes H3O. It's gained a hydrogen ion. So once again, HCl is our hydrogen donor, so that makes it an acid, which makes our water the hydrogen ion acceptor, which makes it the base. So once I know this, the conjugate acids and bases should be easy, assuming you remember that the names switch. The acid, what was the acid, HCl, now becomes the conjugate base. And what was the base, H2O, once it's gained its hydrogen ion, becomes the conjugate acid. So you just need to remember that the name switches. And the reason why it switches is because look at this double arrow. This is a reversible reaction. So this hydronium ion and this chloride, can react to produce liquid water in gaseous hydrogen chloride. So in this case, in the reverse reaction, the H3O is giving the hydrogen ion or donating the hydrogen ion to the chloride, which makes it an acid in the reverse direction. And the base is accepting that hydrogen ion from the hydronium. That makes it a base in the reverse direction. So that's why the name switches. Here's another one. Go ahead and pause the video and see if you can label who the acid, who the base is, and who's the conjugate acid and conjugate base. Okay, so let's see how you did. H2O is our acid because we see that it was H2O on the left, and on the right it becomes just OH minus. So it's lost the hydrogen ion, which means it's donated its hydrogen ion to the NH3. The NH3 must be our base, which makes our hydroxide on the right our conjugate base. It's what the water became. Our acid became the conjugate base. And our base, NH3, becomes the conjugate acid. Okay, one more. See if you can label this one. All right, so the HCl is our acid because it's donating a hydrogen ion. If I look to the right, I can see that it's lost a hydrogen ion. It's given it to the water, and the water has gone from H2O to H3O. So the water is accepting the hydrogen ion, which makes it the base. So therefore, our chloride is our conjugate base, and our hydronium is our conjugate acid. So as you can see in the last example, water was an acid, and then in this example, water is a base. So water is special in that it can both act as an acid and a base. That is called an amphoteric substance, and water is one of the only things that can do that. Okay, so in summary here, there are two separate definitions that you need to know for acids and bases. The Arrhenius definition is based on hydrogen ions and hydroxide ions. The acids donate hydrogen ions, or they give off hydrogen ions, and the bases give off hydroxide ions. The Bronsted-Lowry, or as the Regents will say, the alternate definition is based on the transfer of hydrogen ions. Acids donate hydrogen ions, and bases accept hydrogen ions. You also need to know the acid-base pair. So if you're a Bronsted-Lowry acid, that means you become the conjugate base. And if you're the Bronsted-Lowry base, that means you become the conjugate acid. So those are the definitions for acids and bases, a very common Regents question. We will practice these in class, but if you have any questions, please let me know.